what the mystery of this. We're looking at viscosity versus molecular weight, or number average molecular weight, and then Travis, you also found something, right?
Yeah.
That there should.
So I think the second relation only works if the elution volume is the same, and elution volume is defined as the viscosity times molecular weight.
Okay.
So you tack on another m term, which is why it's 1 plus a.
You said same elution volume?
Yeah.
So, the last way, and maybe the way that most chemists most like to do molecular weight characterization is with NMR. So, with NMR, we have, we can do N-group analysis. We'll do a little bit of a refresher in this packet on NMR. And so NMR can give you N-group analysis, which gives molecular weight. And this is a number average molecular weight. And it also can give you purity and composition of a copolymer. So basically what we do is we take our polymer, a good polymer solution, in a deuterated solvent. So we have a long skinny NMR tube, and in it we will put our polymer solution. And we're looking at, as the M being magnetic, we're looking at the magnetic spin state of the nucleus. So NMR is nuclear magnetic resonance. And usually we're looking at proton NMR because that's the greatest abundance. So here we take our polymer and polymer solvent in a good solution, and we put it in a deuterated solvent. So something like H2O, or you'll be using Cl3, chloroform. And we do this because the solvent, there would be so much more solvent proton than your sample proton, and so we take away the solvent signal by putting it in a deuterated solvent. reduce it. And so that starts here with an NMR chart. So basically what you end up with is a spectra that looks something like this. And where each of these peaks are tells you about the environment of the protons. So if we kind of flip ahead a little bit to look at ethanol here, we're able to, with ethanol, take a few kind of looks at the molecule, and while looking at the molecule, we can identify unique protons, and then you can predict the chemical shifts using that table on this front sheet. More kind of helpful than the table is my table that I keep in my brain. The table is something that you will get on the exam, so you don't need to clutter your brain with this. But I kind of like to simplify it. So if you see a peak at around like 12, this is usually a carboxylic acid, so that H right there. You see a peak at around 10, usually an aldehyde. That guy there. If you see a peak around 7, this is usually aromatics. Around 5, this one's going to be really helpful for us in this class because this is where alkenes show up. And with radical polymerizations, you start out with an alkene in the monomer, and then you end up with no alkene in the polymer, so you can actually use that alkene peak to monitor the radical polymerization and see if it's done. So if it's around 5 and it's broad though, it's usually an OH. If it's around 4, that could be next to an ether. Around 2, next to a carbonyl.
Does BR stand for broad?
Broad, yes. And then down at 1, that's going to be just normal alkene. So basically, if it has something more electron withdrawing next to it, it's going to be more deshielded and higher numbers. And then down on the flip side, if you don't have anything electronegative or electron withdrawing, that's going to be lower numbers or shielded. Okay. So, kind of keeping this in mind, and actually probably you guys, let's just take this nice little reference sheet off the front so that we can look at it as we go and do our fun work of looking at the polymers. Okay. So so they're tumbling very slowly in the NMR, and this averages out the environment, so you have a bunch of different environments, and therefore you don't see the splitting because the peaks are so broad. They're going to go away. So we see those are peaks between 5 and 6. These peaks up here around 7 correspond to the aromatic ring here. And when we polymerize, we see in that box, after polymerization, there are no more alkene peaks. Instead, we now have an alkane on the polymer backbone. It's still a little bit higher than just kind of our simple alkene here, which we said was around 1. That's because it's kind of near that aromatic ring, which we said serves to de-shield and move the peaks to higher numbers. So we would take this unique peak A from the last slide. Call this A again here. And we said NMR is quantitative. So if we integrated and peak A had an integration of 2, and peak, we'll call it D over here. Peak D has an integration of 30. That means there's 30 of those peaks to every 1, or every 2 of those peaks. So if the ratio ratio of monomer to initiator was 1:1, it would be 5:2. So because it's 30:2, that means we have to have 6 repeat units here. We're going to go through some examples on that, but are you following along so far? I'm not getting nods from everyone, so let's take a step, and someone feeling brave and want to tell me how I can what's confusing. Yeah. Yeah, okay, good. Thank you. That's a good place to start. So, if we had, so for the 5:2, what we're looking at is this is 1, 2, 3, 4, 5. So 5 H's for 1 styrene. And then this is our styrene. And then for our initiator, we would have this is kind of the squiggle coming off there. We said A is that guy there, so there's just the 1, 2 H's right there. So basically because you know that for every 5 of those there's 1 monomer unit, you then set up an equation to solve for N. And what you do there is you take 30. I don't have this equation written down, so give me a second to let me make sure that I don't screw something up. So it would be like 30 over 5 equals N over 2. Does that work out right? Nope. Let me see. I think I might have equations set up later. Nope.
I think it should be unique protons, right? So there's only 15 unique protons on the styrene aromatic.
Huh?
Instead of 30, it should be 15, right? Because then you get 6.
It's just integration.
Yeah, it's an integration of 30. So there are 30 aromatic protons. So 5 times 6 is 30. And then if there's one of those, 1 times 2 there. So back when I was a student, one of the professors I TA'd for said that as you get closer to the board, you get stupider. And I was like, you're bullshitting. And then I started teaching, and I was like, nope, no, I definitely do. Things that you know. Suddenly, when you're standing in front of a classroom and trying to explain it, it's like, so. Thank you for help. Does that now help explain where that came from better? We're gonna see a few more examples. Yeah.
Why does D have like, the splitting was kind of weird?
Yeah. Because this is a different environment here than this. Additionally, this is a different environment than this. So basically, ignoring splitting will just make your life better in polymer chemistry. Okay. So these are block and random copolymer that we have made. So what we are going to do with this is essentially come up with something like this, where we're going to look at the integration of that peak versus that peak. So this is at 3.6, we have PMMA, and at 4.06, we have PBMA, and which should be 2 H's, and this one is 3 H's, and we can compare the integrations to tell us about the composition of the block and the random copolymer. We'll call this guy now A, this guy B. Get down here now, we're looking at this guy as A, this guy as B. And you can see, again, the guy on the end has a different environment than the guy in the middle. So that's why you have those kind of split out. And then that guy has a slightly different environment being next to that. So we can compare these ratios though to tell us, because in our polymer, let's just say, I'm sure you figured out from the length of time it took you guys to dissolve your polymers last Wednesday that you have more than 6 repeat units there. So your polymers are longer, and so you won't really see those side peaks there. You're just going to see your major peaks. So we can use, yeah,
Are B and A flipped on your spectrum, the way you labeled them?
probably, yes. There we go. Okay. So, the NMR can tell us 3 things. Identity and purity of the polymer. So, did we make it, and is it clean? Copolymer composition. So we can tell monomer ratios, how much acrylate or methyl methacrylate we have compared to butyl methacrylate. And then it can also tell us the molecular weight with end group analysis. And so we will have a few examples of this that I think we'll start next time. Actually, after having been in the lab and seeing what the NMR looks like, I think it might make a little more sense at that point to talk about how to tell these things in our polymer. Does that sound good? Making it a wrap there for tonight. Okay. Before I
just making the samples, or are we also running them?
No. So the NMR, you're going to learn how to run it, and then Zoe will run it for you. Because unfortunately, meeting with Roberto for part of the class doesn't quantify or classify it as training. And so if you are NMR trained and want to run your own sample, you by all means can. But otherwise, Zoe will put it in for you, and you'll see our NMRs are completely automated, so you aren't missing much. You basically drop off a tube, and then the results get emailed to you. And so the only part you're going to miss is physically handing the NMR tube in, and you're going to see an NMR tube be put in anyways, and you're going to prepare the NMR tube. So you will be completely taught how to make your own NMRs, and the experience will be simulated. We may at some point take a visit to the GPC to see the GPC as well. But since that's in another professor's lab, taking a whole class through a professor's lab, it depends on the timing of what's going on in the lab if we can arrange for a trip to the GPC. So some years we have gone to the GPC as a class. Other years it's just been the mystery box that the TA has injected for you. Or even I think last year the Noonan GPC was down, and so we just handed it off to one of the Maniachewski grad students. So my TA didn't even do it.